For Chapter 9, Day 9, we're going to look at inverse trig equations. In order to look at the inverse trig equations, you guys have to know the domain restrictions. So they're all right there. You can take a look at them. Basically, you need to know that if you're talking about the sine of an angle, your domain of that angle has to be between negative pi over 2 and pi over 2, which is quadrants 1 and 4. And then cosine of an angle has to be from 0 to pi, which would be from quadrants 1 and 2. And then tangent of an x, again, that angle that you're talking about has to again be between negative pi over 2 and pi over 2. These domain restrictions come from knowing that, again, in order for a relation to be a function, it has to pass the vertical line test, which all of our functions do. But again, in order for something to be invertible, if you're finding the inverse or using the inverse, it has to pass the horizontal line test. So as you can see here, if we have the sine function and we just leave it alone, this would clearly not pass the horizontal line test. So in order for it to pass the horizontal line test, what we do is we place these domain restrictions. So from here to here, negative pi over 2 to pi over 2, we can now pass the horizontal line test. Same thing for cosine of x from 0 to pi. In order for it to pass the horizontal line test, we're only looking at that domain restriction from 0 to pi, which again would apply to quadrants 1 and 2. This would mean that if you're finding the inverse of these trig functions, you now have a unique output, a unique ratio. Okay? So keep that in mind as you're doing these. Now, if we are trying to find the arc sine of pi over 2, a good example here would be, because it's in our domain, you can find sine of pi over 2, it's 1, and then arc sine of 1 means what is the y value, what angle has the y value on the unit circle equal to 1? Well, that occurs at pi over 2. Okay? Using our properties listed above here, as long as our angle is in those domain restrictions, these two can essentially cancel and you're left with the inside angle. This is going to come in handy when we take a look at example 2, because again, pi over 8 isn't on our unit circle. We don't know the actual output, but because you're taking the arc cosine of cosine, you can apply that property and you're just left with pi over 8. So that's where these properties come in handy, is when you're taking the arc sine of sine or the arc cosine of cosine. You can essentially cancel those out and make it a lot easier on yourself. Now, for a problem like number 3, where you're taking the cosine of the inverse sine or the arc sine of a ratio, we can't really apply that property because, again, these are not opposites. So what are we going to do here? Well, if you notice, remember when you take the arc sine or the inverse sine of a ratio, your output is going to be some angle theta. Okay? So if we go on our coordinate plane, I should be able to find an angle theta where the ratio is positive 2 over 7. But remember what we just talked about. You have to have domain restrictions when you're talking about the inverse sine, inverse cosine, inverse tangent. The domain restrictions for arc sine, arc cosine, and arc tangent are right here. So sine is obviously positive in quadrant 1, but it's only negative in quadrant 4. Remember, this is our domain from negative pi over 2 to pi over 2. Cosine would be positive in 1, negative in 2, because again, that domain is from 0 to pi. And then tangent, again, going back to negative pi over 2 to pi over 2, those are our domain restrictions. So if we're trying to use the arc sine, because it's positive in this case, right? Our ratio is a positive ratio, we're going to be in quadrant 1. Again, for sine, never in quadrants 2 or 3. On that reference triangle, this is our angle. We don't know the actual angle, but we know that angle puts us in quadrant 1. We can create our reference triangle. Now, using this reference triangle, we can now find the third side. 2 squared plus x squared equals 7 squared. X squared equals 45. X would equal 3 root 5. Now we know our third side. So the nice thing about this is we never found the actual angle we're talking about on the inside, but if we just call it angle theta, now that we have the reference triangle, I can find the cosine of theta. Why? Because it's the adjacent over the hypotenuse, So it's 3 root 5 over 7. So by using these domain restrictions, using these properties, and applying the coordinate plane to create your reference triangle, you can find the cosine of some angle. And even though the angle is unknown, if you know the ratio that's created by another trig ratio, you can find the cosine of that angle. Let's apply this knowledge down to number 4 here. Again, this is a little bit of a typo here. But if we have sine inverse of 2/3 on the inside, we can create our reference triangle. We're, again, never using 2 or 3 for sine. Sine is positive in quadrant 1 because our ratio is positive. So the opposite over the hypotenuse would create our ratio, our reference triangle right there, 2 over 3. Using Pythagorean theorem again, we can go ahead and find that third side. X squared equals 5, so x would be square root of 5. This inside is our angle theta. Now that we have our reference triangle, we can find the cosine of that angle because we have our reference triangle built. So the cosine of that angle would just be square root of 5 over 3. And that's the main concept that we're talking about today, besides these properties of matching sine and inverse sine, or cosine and inverse cosine being able to cancel. When you don't have those, you can go ahead and build your reference triangle if you have the arc sine or arc cosine or arc tangent on the inside of these equations. And then from there, you can use those reference triangles to help you find the ratio that you're actually looking for. On the next page, we're doing the same concept, but we're going to notice this time we actually have the tangent inverse. We'll remember, again, for tangent, never in quadrants 2 or 3, and tangent is negative in quadrant 4, from negative pi over 2 to 0. So here's our angle. We're going to call it theta again because the inverse trig function gives us an output of an angle. So we have tan inverse of -1. That's going to result in our angle theta. Now, building our reference triangle, we know that tangent of an angle equals y over x. So we're going to say that ratio is -1 over 1. Again, our y value has to be the -1 because we are in quadrant 4. Use your Pythagorean theorem to go ahead and find that third side. We get square root of 2. Now that we have this reference triangle based around angle theta, we can actually find the sine of that angle we're talking about, which in this case would be -1 over root 2, which rationalized would be negative root 2 over 2. The last problem, and by far the best problem, is down here at number 6. In this case, again, we're finding cosecant of sine inverse of a ratio minus cosine inverse of a ratio. Again, truly understanding that these two are going to produce outputs of angles. Now, because they are not the same, we're going to label them different angle measurements. So we have angle theta and angle beta. Okay, and again, this is determined based on the fact that they are both inverse trig ratios of a ratio, so they give you an angle. So let's go ahead and draw our reference triangle for angle theta. We know that sine has to be in quadrants 1 or 4. Because it's positive, we'll put it in quadrant 1. Use Pythagorean theorem or your special triangle in this case, 30, 60, 90, to find that. We know that cosine has to be in quadrants 1 or 2. Because it's positive, it again is in quadrant 1. Again, using your Pythagorean theorem or the special triangles, you can create that reference triangle by finding the third side. So here are 2 diagrams, both representing angle theta and angle beta. Okay? But where are we going from there? Because in this case, we are subtracting these 2 angles. So we can't really do much here yet because we have to find the cosecant of theta minus beta. So let's go ahead and rewrite this so it's a little bit cleaner. cosecant of theta minus beta. Now, just because we're doing something a little bit different and I gave you some new identities and some new properties, doesn't mean you shouldn't have that formula sheet and those double and half and sum and difference angle identities right by your side. Because if you notice, remember cosecant is the reciprocal of sine, so we can rewrite this as 1 over sine of theta minus beta. Hopefully at this point, there's a lot of bells going off stating that this is a difference identity. Sum and difference. So if we just look at the denominator, we know that this can be rewritten as sine of theta cosine of beta minus sine of beta cosine of theta. Using this identity, we can apply our two reference triangles to help us figure out the rest of this equation. So we have sine of theta, you know, is 1/2. Cosine of beta, we know is 1/2. We know sine of beta, let's go minus, sine of beta is root 3 over 2. And we have cosine of theta is also root 3 over 2. Again, we pulled those from our two reference triangles that we made over here using the inverse trig functions. So now, if we go ahead and simplify this, we have 1/4 minus 3/4, which is negative 2/4, but be careful because we got this fraction up here, so it's not negative 2/4, it's actually 1 over negative 2/4, which if you multiply by the reciprocal would just be negative 2. So cosecant of all that is going to reduce to negative 2. Go ahead and try the homework. If you have any questions, feel free to ask your teacher. Good luck.